Welcome to the Deep Dive. Today we're shrinking down, looking right into the hidden architecture of the materials all around us.
That hidden world, yeah. How molecules decide to pack together.
Exactly. And, for everything from, say, new medicines to better solar cells, the way these molecules form crystals, it makes all the difference, right?
Absolutely. It dictates their properties, how they actually work.
So today, our deep dive is into something called crystal structure prediction, or CSP. And we're focusing specifically on molecular crystals.
A fascinating and historically challenging area.
Right. Because predicting these structures, it's been this huge computational task for ages.
Monumental is a good word for it. You're trying to figure out the best arrangement out of maybe billions.
And the traditional ways, like
Uh-huh.
DFT density functional theory, people say it's accurate.
Oh, it's considered the gold standard for accuracy, yes. Dispersion-inclusive DFT especially.
There's always a but.
The but is that it's notoriously slow and incredibly expensive, computationally speaking. Exploring that huge landscape of possibilities was just often impossible.
Okay, so that sets the stage perfectly for what we're unpacking today. This thing called FastCSP.
Yes, FastCSP, it's more than just a tool, really. It's an open source workflow designed for high throughput work.
And at its heart, it uses is it a machine learning model?
That's right, a machine learning interatomic potential, or MLIP. This one's called UMA, the Universal Model for Atoms. That's the engine.
Right, UMA. So what's our mission here today? What should listeners take away about FastCSP and UMA?
Well, the mission is really to show how this combination is dramatically speeding up crystal structure prediction. It's like finding a shortcut, getting insights that were just out of reach before.
A shortcut, I like that.
And it's so critical for material science. Think pharmaceuticals, organic electronics. We want to show why this acceleration matters so much.
Okay, so let's dig into that bottleneck. You mentioned DFT is slow. Why exactly? What makes it so computationally heavy?
Well, DFT works by calculating the quantum mechanical interactions. Basically, it looks at every electron, every atom, very meticulously. It's incredibly detailed.
Which sounds great for accuracy.
It is, but it takes a huge amount of computing power and time for each calculation.
And FastCSP with UMA. How does it, get around that? What's the fundamental shift?
It's a totally different philosophy. UMA, this MLIP, it's essentially a very smart AI. It's been trained on vast amounts of data.
Like this OMC25 data set mentioned in the research.
Exactly, like OMC25, which is a huge library of known molecular crystal structures. UMA learns the patterns, the relationships between atomic arrangements, and their energies and forces.
So it's not calculated from scratch every time.
Precisely. It predicts based on what it's learned. That makes it orders of magnitude faster. Seriously, orders of magnitude.
Wow. Can you give a sense of that scale difference?
Predicting a single complex structure used to potentially tie up supercomputer resources for weeks now. With FastCSP and UMA, we're talking about screening thousands, maybe more, in hours or days using, say, tens of modern GPUs.
That's genuinely a leap. So it's not just faster, it's a different way of seeing the problem.
You could say that. It allows us to tackle problems at a scale we couldn't before.
So what new capabilities does that scale unlock for researchers? What can they do now?
The real game changer is high-throughput screening and discovery. It's now feasible. We can explore enormous chemical spaces. Meaning we can computationally design and test countless hypothetical materials, predict their stability, their properties, before anyone tries to make them in a lab.
So less trial and error, or targeted design.
Exactly. Designing new drugs with specific properties, creating more efficient materials for organic solar cells or LEDs. It becomes much more rational, much more guided.
That sounds incredibly powerful. Is it perfect, though? Are there maybe trade-offs compared to the rigor of DFT, or situations where it might struggle?
That's a fair question. Look, FastCSP, powered by UMA, has shown remarkable accuracy, really achieving DFT-level precision for predicting structures and their relative stability in many, many cases.
But not all.
Well, for maybe extremely unusual molecules or very exotic bonding situations, you might still want to do some initial, more intensive DFT checks, perhaps. But for the vast majority of systems, especially those relevant to pharma and organic materials,
good enough.
It's more than good enough. It provides that DFT-level accuracy at a tiny fraction of the computational cost. As I said, hours on GPUs versus potentially months on supercomputers. That's the trade-off, and it's usually a fantastic one.
Okay, so let's recap the sort of aha moment here. We have FastCSP running entirely on this UMA machine learning potential.
Yes.
And it's giving results, structure predictions, stability rankings that are basically as good as traditional DFT.
For most relevant systems, yes.
But doing it incredibly faster and cheaper.
That's the core takeaway. Hours, not weeks or months.
And maybe just as important, you mentioned it's open source. FastCSP, UMA, even the OMC25 data.
That's right. The whole package is being released openly.
So what does that mean? What's the so what there?
The so what is huge. It dramatically lowers the barrier for researchers everywhere to use these advanced techniques. It's a democratization, really.
Democratization of computational chemistry.
Exactly. High-throughput crystal structure prediction isn't just for a few big labs with massive computing resources anymore. It opens the door for accelerated discovery across the board.
Which leads to a final thought, maybe, for you listening.
Yeah.
Consider this newfound speed, this accessibility.
Think about the possibilities.
Yeah, how might understanding molecular structures this quickly unlock entirely new kinds of materials, new products? What industries could be transformed? Pharmaceuticals, sure, electronics, energy, but maybe even fields we can't quite, imagine yet.
It really could accelerate breakthroughs in ways that are hard to predict right now. It's an exciting time.
Something definitely to think about.